I really want this class to be, in fact, I wanted all classes to be fully interactive. So I want your inputs throughout. So just be focused, because as I said, I actually wanted to do this the previous week. What I said was like the flagship class of this entire course. So in that sense, because you're going to get a big picture of structural analysis, and whatever we are going to do in the remaining 6 or 7 classes is essentially a special case of what we are going to do today. So I really would like to have your inputs based on what you have done as part of this course, as well as the courses that you have done in a related manner, like deformable bodies, statics, dynamics, etc. So we are not going to get into any problem solving or whatever right now. We're just trying to get our concepts clear. Okay, so then you'll see that lots of the equations and other things will fall into place much more easily than if they were learnt as let's say individual isolated entities. That's the whole idea of this. I'll get into the slides, and I want your complete focus and a lot of inputs that I'll be seeking from you in an interactive thing, which is why I've drawn this table over here. It's a headless table. I have not yet named any of these columns. We'll do that once all your inputs are in place. Right now, I'll seek a few inputs. I'll post the questions on the PowerPoint slide, and when you give me your inputs, I'll start populating these tables without the heads, and then eventually we'll get to the heads, right? So this is what I call as the big canvas of structural analysis, in the sense that it's like almost like a painting that we are doing, but in terms of words that we are trying to put together and stitch and see a story behind it in terms of what structural analysis is all about. Then based on what you have learned as part of this course, the prerequisites, as well as what you're going to learn later on, you will see that things fall together in a very integrated manner, and you'll start appreciating structural analysis in a very, very holistic sense, right? So once we are done with that, we will see, maybe hopefully in the afternoon class, we'll get into certain basic structural elements, which will become like the simplest cases of what we are whatever exercise we are doing right now. And then we will then connect them and all those each individual elements, and then see how the load is going to get transferred from one type to the other. So that's the overall summary of what we are going to do today. Okay, so the first question that I'd like you to answer, and don't take this as anything challenging, it's fairly straightforward and simple questions that I'm posing, which pretty much every one of you will be aware of. I'm just asking in terms of all the homeworks that you have done, all the exams that you have done, all the lectures that you have listened to, not just mine, but as I said, deformable bodies, statics, dynamics, etc. What are all the kinds of variables that you typically see in a question? For example, if it's a question you're answering in a homework or an exam, there's certain input data which is given to you, certain output which is expected of you, and you have some laws or equations which help you to solve some in terms of the other, right? So right now, let's not go into the equations or the laws governing it. We'll just talk about the variables. Typically, what all inputs are given to you and what all outputs are you are expected to produce out of it. And we will not distinguish even between input and output. We will talk of all the variables which are connected. Some might be given, some might have to be found. Okay, so that's the whole idea of any problem solving. And so the variables in particular that we are interested in over here is those which describe the state of a mechanically loaded structure, which is what structural analysis is all about, deformable bodies is all about. You have a certain structure and you have some kind of a mechanical loading on it, which is why it's called a loaded structure. Of course, there can be other types of loads, non-mechanical as well. We'll not bother too much about it right now, but what are all the variables which describe such a structure? What kind of inputs you typically see, what kind of outputs you see? So can you start throwing up a few words so that I can start filling these tables? Yeah, Harish. Length and mass, yeah, of the structure. Okay. Just there might be certain quantities which I might probably fill in multiple places. Well, there's a reason why I'll do that, because right now there's no heading for the table. So what she says is that sometimes the mass might be given of the structure, sometimes the length might be given, or they might have to be found giving some other parameters. So anything else that you can think of. Yes, Alexa. What's that again? Density. Yeah. So glad you saved me that repetition. Okay, and density we are using in the sense of mass per unit volume here, but because we are also familiar with the other concept of strain energy density that we already saw, so we're not going to look at that right now. So by density we mean the kilogram per meter cube SI unit stuff, right? What else? Yes. Okay. So I'll just list it as E. Okay. So we've been seeing that whereas for isotropic materials, just a single valued quantity. In the case of the composites and typical materials that are currently used, it's an Young's modulus which has a directional dependency that E1, E2 and E3 can in general be different, right? So let me list that out there. What else? Poisson's ratio, okay. So once again, you don't have a single Poisson's ratio, but 9 of them typically, not all of them are different from each other, but essentially you have this as well. What else? So far most of the things that you have been talking to me is kind of a description of the structure itself, right? So which is why you see only some of the columns are getting populated, but there are also certain other things that you typically do. You're not just given the geometry of the structure that and what it is composed of, so the material properties, right? So what else is typically given or asked out of you? Shear, okay. Shear what? Shear force, shear stress, because shear force. So let me take advantage of that, and since you all mentioned shear, we could also talk about the shear stress as well. Let's say tau ij, right? What else?
Maybe the boundary conditions or constraints.
Yeah, good. Okay, first I'll do something and then I'll get back to you on that. I'll use the abbreviation BC to refer to boundary conditions, and I'll put it in multiple places and we'll see what. So Patrick, can you qualify by boundary condition? It's not a single type of boundary condition, right? Multiple possibilities are there. So what examples can you think of boundary conditions?
So an object could be like pinned at a certain point.
Yeah.
Or you could have a free end.
Good, yeah. So, for example, when it is a free end, what quantities are you specifying at the free end?
You might find like deflection, there's a force at a free end.
What do we mean by something is free? So essentially, it's not kind of constrained, right? Like the other example you gave is of the hinge or whatever, where you're constraining the motion in some manner. Here you're not constraining the motion, it could just be free, which means that essentially whatever forces or moments are there can be specified, or they can even be zero, right? So whereas for the hinge, what are the typical conditions that you have?
Usually it's not able to move in some
Good.
direction.
So if it's not able to move, then you're essentially what you're constraining is the displacement, right? So you're essentially saying that it could not move in a particular direction, or maybe in all the directions also, right? So some of the boundary conditions are what we call as the natural boundary conditions, and some are called as the geometric boundary conditions. So the example that you gave of, let's say, the free end, where the forces and moments are known quantities, essentially comes under what is known as the natural boundary conditions. So in other words, you are specifying those boundary conditions in terms of forces and or moments. Okay, so you're specifying the F and M at some values of the spatial coordinates, whatever x, y, z are, at some x naught, y naught, z naught. You are specifying the forces and moments, whereas geometric boundary conditions, what we mean is that we are specifying either the, let's say, the displacements or even the slopes, which is essentially the rotations. You are trying to specify them at some x naught, y naught, z naught, right? There can be certain x naughts, y naughts and z naughts where in other words, certain parts of the boundary where you are specifying one natural and one geometric also. So the hinge example that you gave is a situation where you have the possibility of no displacement, but it can allow rotation, which means that you are essentially specifying the moment at that point. Okay, so so in other words, your specification of the moment is a natural boundary condition. The specification of zero displacement at the hinge is essentially a geometric boundary condition. So this is how boundary conditions are typically separated out, and so there are certain specific names based on the people who did a lot of work towards that, Dirichlet and Neumann, and then you have combined forms of that called Robin boundary conditions or Cauchy boundary conditions, etc. We'll not complicate things like by that all those names, because essentially that's not explaining the physics or the math, but just honoring the people who are involved with it. What is more important is that when we say natural, essentially we're talking about the forces and moments. When you're talking of geometric, you're essentially talking of the geometric quantities like displacement, rotation, etc. Right? So that is a good thing, a good point you brought out. Boundary conditions. What else? Think of all the problems that you have solved as part of your homeworks, as in deformable bodies, statics, dynamics, etc. Yeah. Twist. Yeah. Very good. I like it when the first entry goes into any column, so because you're trying to give a new perspective to this whole thing, right? So what else? Yeah.
The twist also follows like torque as well.
Good. Yeah. Torque is causing the twist. Twist is an effect of that. So torque is the moment. So essentially you are applying a load and then it's changing by a certain angle. That angle is called twist. So twist is in radians or degrees, whereas torque is in Newton meter. Anything else? Bending moment, yeah. Okay, what else? Yeah. What again? Internal stress, yeah. So other than shear stress, which was already mentioned by Nilesh, Alexandra is talking about the other stresses, which could be the normal stress, right? So it's all, and stresses by nature are kind of internal to the structure. Of course, they are existing on the boundaries as well, but essentially it's something that's happening with the material of the structure. It's not an external load. Okay. So in that sense, we will see these quantities. It's a little here and there, kind of amphibious. So you would find that sometimes we will see why I'm doing this. Just like in the case of mass, I first put it in both places, but once Alexandra said density, I removed the mass from there and put density over there and retain the mass over here. So like that, we will see how when this probably can be split as well. So what else? Come on, guys, you've done full courses related to this. I'm sure you know many more variables. Strain, yeah. So Arya gets a lot of points for populating the first one in multiple columns. Okay, so let me, since I'm using symbols, let me use a symbol there as well. So can you say in terms of corresponding quantities that we have already listed, a normal stress and a shear stress, what do you have in, as the counterparts in the strain? Same, right. So we call them, let's say gamma II, and typically we put a 2 to refer to an engineering strain, engineering shear strain as gamma ij, where you do not have I equal to j, which was already taken care of, right? So yeah, come on, I really want to run out of space on this board. Yeah, strain energy, very good. In one of the assumptions that we were making, we introduced the concept of strain energy, but we said something more. What did we say? Existence of? Yeah. So let me say that SED is what fits in here, whereas the strain energy is also an important concept, which is essentially an integration of that over the volume of the structure. So that may not necessarily fall only under that column, which is why I just wanted to qualify that. Yeah. Yeah. Friction. Good. Yeah. Okay. So you can think of friction as an external force which is coming onto this because of another surface which is coming in contact, and there's essentially a surface roughness between them, and which is essentially acting like that, right? You can also think of if both those bodies which are in contact with each other are part of an overall system and they are like subsystems of that, then it's kind of becomes an internal force for that system, and then I could probably put friction here as well in this column, but right now I'll stick to this, that is essentially in contact with something else. But contact, interestingly, is also a kind of a boundary condition in the sense that essentially what's happening between two surfaces, so friction can find a place here as well. It might sound a little strange why I'm talking about where it fits in, even though I've not named what those columns are, but you will see that a little later once we populate with more variables. Yeah, what else? Malleability, okay, very good. Yeah. Yeah. What else? Think of all the questions that you have faced in homeworks or exams. What was the input given to you? Then what was the output asked out of you? So you can remember some of the variables. Strain?
Strength.
Strength, yeah. Good. What else? So multiple types of strength could be there, the yield strength or the ultimate tensile strength or the shear strength, etc. So just clubbing all of that together over there. Yeah. What else? Think of statics, dynamics as well, not just deformable bodies. The courses that you have done in statics, dynamics, deformable bodies.
Melting point.
Okay, good. Okay. Actually, some of the questions that I had are also getting answered here. So let me just kind of move on. Keep this question in mind. Okay, so we're not done with this question as such. So as you think of more variables, will start populating over here. But we will share the other questions as well, so that you know why I'm kind of populating the other columns as well. Because not all of these are variables, remember, they're not all kind of variables, there are some constants involved as well, etc. And also something like a boundary condition, more like an equation rather than a variable. So I've just populated as and when you gave me the inputs. So some of the questions for that have already been asked, or you have taken it for granted that has been asked. So the second question that I have is, okay. So maybe I'll not look at that. Yeah. Okay. So in terms of the variables that you have listed, so you could probably classify them into 4 general categories, and the variables are essentially this is the first column of variables, the second column of variables, a third column of variables, and a fourth column of variables. So I'm categorizing different kinds of variables already, but the ones that I have not yet numbered are essentially not variables. For example, these are like equations. These are also like equations. Some of the are connecting things, and some are constants, essentially something to do with the material itself. So we are looking at those not as variables, right? So the idea is that, is it possible, first of all, to list all the variables that we have come across? It's not like just word jugglery, right? So all of these have certain precise meanings when we use them in science or engineering. So there has to be some purpose behind each one of them, just using them just like that, right? So then we have looked at some kind of a classification there, but we'll come to more of that as we move forward. Let me look at let's look at the other question as well. So the question that we have is in terms of, because we have these 4 sets of variables, obviously we should have some equations which are kind of connecting them, or certain quantities which help us to connect them. So essentially usually I would like to have a color coding for this, but let me instead use a shape, put these in, let me use Roman numbers. So this is what this question is all about. Is there some way of connecting these quantities that we have kind of listed in the circled columns? And that connection could be in the form of equations, could be in the form of constants which are relating it, etc. So essentially we are looking at 3 sets of equations which have been numbered using Roman digits. So relating 4 sets of the state variables which are circled over here, the Latin form of the numbers, right? So now we're not kind of done yet. As I said, even this board or much larger boards will not be sufficient to completely or comprehensively carry out this exercise. Maybe that will never be possible. So let's think of certain things which have not yet been populated much, for example. So you can think of some quantities similar to twist. Deflection, good. Yeah, what else? Any other? So deflection is more like something which has the units of length, and twist is something which has the units of an angle, radians, let's say, right? So can you think of any other angular quantities and any other length kind of quantities that we can list over here? That what is the effect of doing such an exercise, right? So already when we talked about, Nilesh mentioned twist and torque, so then we said there's some kind of a correlation where torque is the cause and twist is the effect of it. So can you think of any other such quantities which have a 1:1 correspondence, like torque to twist? Something is to something else.
Like viscosity.
Viscosity, yeah. So let me put that here. So essentially property, you can think of coefficient of viscosity or whatever. So essentially you're looking at that. But of course, there are other things associated with it, like a viscous force that could happen, a viscous stress that could happen, and because of that viscosity, you could have a boundary layer forming, etc. So all that is there, but just for convenience, we'll put it here alone now, but it could find place in its many forms in other columns as well, right? Yeah. Let me also get the final question out, and then we will start looking at it. So we saw there are certain variables which were circled numbers that you see in the odd columns. That is essentially your first, third, fifth, and seventh columns. Essentially, you're looking at what is the variables, and then we're talking about the ways in which these can kind of be related to each other. So in other words, we're talking of the equations, right? Now, what do these equations depend on? Okay, so all these quantities that you listed already, for example, mass, you listed length, etc. So it's not just equations that I'm listing in this boxed quantities, but also what those equations involve in terms of constants or typically the input properties which are given to you. So, so can we think of some more variables to kind of have more examples of each one of them, so that we can then see the bigger picture better. Moment of inertia, good. There are two types of moment of inertia. One is essentially a purely mathematical thing. We're talking of the length, like what we deal with in, for example, dynamics kind of situation. Also, there's also something that is involving a weighted moment of inertia, which is involving the, let's say, the material properties as well, like the density to get the mass into picture. Like, so I'll put it over here as well. So these are two different kinds of things which are given the same name, unfortunately. So, but they have kind of different properties. So one is essentially what I'm putting here is like an x squared integral of an x squared dA, for example, whereas here x squared rho dA, where rho is the density of the material as well, which is involved. And this is what we will use more often in this particular course rather than that. So what else?
Torsion and displacement.
Yeah, okay, yeah. So torsion is something that we already listed as torque, and the torsional displacement is what we already talked about as twist. Yeah. So multiple different names could be used for the same thing. Let's go course by course, maybe look at statics. What type of questions you were asked? What were the inputs? What were the outputs? Typical problems in statics. What's given to you and what you're asked for.
So usually, like, there'd be like a gravitational force on a body.
Mm-hmm. Yeah.
That body might be facing like some sort of bending moment, which is listed.
Yeah. Bending moment we already listed there. Okay. Good. So you talked. We mentioned friction, gravity, anything else, something like that, which is causing the load on the reaction forces. Good. Yeah. So to some extent we have covered that in the natural boundary conditions, because Patrick mentioned the hinge, for example, where there is essentially no displacement, which means there has to be a reaction force coming up there, right?
spring forces and
Very good. Yeah. Yeah. So let me see where I can put that. Maybe. Yeah. So we can think of the spring force over here and some property of the spring itself. If it's a linear spring, we call a spring constant, for example. So I'll break that up into two. It could also be a nonlinear spring, in which case it's not a constant, but some properties associated with the spring which could come up there, right? Potential energy and kinetic energy. Yeah, good. Yeah. Both are energies, but they're interestingly falling in different places. Of course, we have certain quantities coming from other places as well, but for now, we will look at it that way. What else? We can move on. So since you brought in kinetic energy, we can move on from a course on statics to dynamics. So you remember some of the variables that you used in the dynamics course.
velocity.
Very good. Yeah. So yeah. What are their angular counterparts? You don't only have a translational velocity and translational acceleration, right? What do you call the angular counterparts? Angular velocity and angular acceleration. So typically you use symbols like V, A, omega and alpha for those. Yeah. Good. What about the course on deformable bodies? What kind of questions are you familiar with in terms of what's given to you and what's asked for as well?
There'd be like, there'd be some problems where there'd be like heat applied
Mhm.
onto
Yeah, yeah.
body.
Yeah, yeah, okay.
So you'd see how much deform over time.
Sure, sure. Yeah. So right now we are kind of sticking to mechanically loaded structures, but since you brought it up, we could include other fields as well. So that's heat, even though it's not a mechanical load, but it can cause certain mechanical changes in the structure, and therefore it plays a role in structural analysis, a big role in fact, many problems. What else? Power, yeah. Yeah. So let me see where I can kind of put it. Yeah. So we already talked about certain energies like potential energy, etc. So essentially you're talking of power in a sense of the time rate of change of the energy or the work done, etc. So I'll put it over here for now.
Work.
Work, yeah, yeah. So work is something that gets done when you are applying a force, and it moves the point of force, point of application of the force moves in the direction of the force by a certain distance, or it could be an angular version of that, where you have a torque and then that is causing twist, and therefore some work done based on that, right? So let me put all of them together as some work done, WD.
Coefficient thermal expansion.
Very good. So we typically, even though we use alpha for angular acceleration, we use the same symbol alpha typically for this as well. But in the case of anisotropic materials, just like your E's and U's, this will also have certain coefficients which are associated with that. Okay. So thermal coefficients of expansion would be your alpha II, and it could also cause certain shearing deformation, which is kind of very rare, but mostly you would have the alpha 1, alpha 2, alpha 3 in the 3 orthogonal directions, which could in general be different from each other. Yeah. What else? Inertials, initial stress, yield stress. Yeah, yeah. So yeah, so we kind of talked about strength over there. So that includes both, let's say, ultimate as well as yield. Okay. Come again? Very good. Yeah, yeah, yeah. So let me see where I can put that. Yeah, impulse and momentum. Yeah. And momentum once again could be either translational momentum or angular momentum, which we'll call as L and H. Yeah. What else? Maybe I can put kinetic energy here as well. I cheated on you. Anything else? So don't just think of variables, think of the equations which you needed to solve for them. What all equations you needed to solve? Or laws that you needed, which laws that you used to solve them.
Is there also like engineering stress?
Yeah, so different types of stresses are possible. So it's not just normal and shear is not the only kind of classification, but we could have many other types of classification as well, including engineering stresses, as you mentioned. Okay, depending upon what you choose for the strain, how you define the strain, there will be a 1:1 correspondence between the stress and the strain. There will be certain conjugate pairs, and many a times that will be determined by the strain energy density definition, and or in more complicated problems where strain rate comes into picture, dynamic problems, you could have the power strain. The power that is coming out of that, I could call it SPD or strain power density, could also be an important thing which is kind of linking them. So that's one type of stress, and similarly you could have the correspondingly, you'd have engineering strains as opposed to tensorial strains, but there could be many others which are named after people, typically like Jaumann, Cauchy, Euler. You have Cauchy stresses, Piolo, Kirchhoff, and things like that. So let's not complicate things with names of people. It's more in terms of understanding the physical parameters, which is why we're listing this. Yeah. Which is why when you say Hooke's law or something like that, instead of that, I would rather prefer to list this out, even though that's also named after a person, Young's modulus. But we just want to focus on the actual physical quantities involved.
Bulk modulus?
Come again?
Bulk modulus?
Bulk modulus, yeah. Good. The middle column seems to be the most popular, and most of the inputs for that given by thanks to Nilesh. Let me see some of the ones which are least populated. Let's say something like twist or deflection. What are the quantities are kind of similar to that in nature? Rotation, yeah, good. So one type of rotation is twist, but there could be other types of rotation as well. So for example, if I talk of this as a rod and I have x1 along the length, x2 and x3 along the cross section, a rotation about x1 is essentially twist, but there can also be a rotation about the other directions, right? So which is what rotation is generally. So in that example, I can call this as theta 1 or theta x, and theta y and theta z, or theta 2 and theta 3, the other direction rotations as well, right? What else? Think of equations which connect, which you have used those equations to solve some problems, or laws that you have used to solve problems.
Yes, Newton's laws.
Yeah. So okay. So essentially, what are Newton's laws? You're talking about some kind of a connectivity between the forces that are acting on the system with the mass and the acceleration, etc. That's the second law. Then, or you're talking of the third law, where you're talking of equal and opposite reactions to an action. So essentially, once again, you're relating the forces over there. And the first law can always be thought of as a special case of the second law, where you're setting the acceleration equal to 0, and therefore saying that a body which is at a constant state of motion, whether at rest or at constant speed, continues to be so under when no forces are acting on the system, right? So essentially, you're setting F equal to ma. If you're setting F equal to 0, and you're essentially dealing with ma over there, right? So if a is 0, then obviously velocity should be constant. What else?
I guess also, Euler's laws as well.
Yeah, good. So the rotational equivalent of the Newton's laws are called as Euler's laws, or rather rigid body extensions from particles. Relativity, yeah. Relativity is essentially a topic, but what specifically you mean?
Like specifically, like how you view how like forces are moving relative to a body. No.
Okay. So essentially, you're talking about forces which are functions of time, right? Or functions of time and space as well, right? So essentially, let's put forces in general as functions of x, y, z, and t, right? And it could be in a generalized sense where you're involving the moments as well. So frame of reference, very good, yeah. Let me see, where do I put that into? Associated essentially for this to be valid, otherwise Newton's laws wouldn't be valid if it's not an inertial frame of reference, for example. So let me just put it here for now, but it will be required in other places as well. So we have some constants, we have some variables, we have some equations. So still, I'm not happy with columns 2 and 4. Not too many guys up there, right? So what else can you think of over there? Buckling, yeah, very good, yeah. Yeah, so we can think of in terms of the critical buckling load. Depending upon the size and shape of the structure and its boundary conditions as well. Yeah. Stiffness? As you want to qualify that in something, because we already have some quantities like E already which kind of represents the stiffness. Anything else you have in mind? Right, the E is not the only stiffness, you're right. So what other examples can you think of? We have already looked at one of them, which was supposed to be your homework for today. You guys haven't done it. So you're supposed to prove C44 equal to C22 minus C23 divided by 2, and which is an equivalent of G equal to E by 2 into 1 plus nu. We have listed E and nu, but we have not listed G. So what Alexandra says is another kind of stiffness which I can list out as Gij, right? The shear modulus or shear stiffness.
Force, could you distinguish between concentrated forces and distributed?
Yeah, sure. Yeah. So both of these quantities could be either concentrated or distributed. And you can go one step further. One is when you say concentrated, it's acting at a point typically, and say distributed, it's acting along a length or an area. But you could also distribute it over the volume. What do you call that in that case? Pressures over a surface. Okay, so that's so it could be an external pressure, which also I'll list out here. So it's like, for example, if I'm applying a load over here, it's at a point, concentrated at a point. I could use a distributed load, but it's kind of distributed along a line. So it's a line distribution. So the first one was, let's say, in newtons. This is in Newton per meter. And then the third example that you gave, external pressure, which is Newton per meter squared or Pascal. And but you could also have Newton per meter cube. So what do you call such a force? Yeah. In fact, one of the assumptions we made was no body moments, right? So which helped us to simplify the problem or model. I guess we have a reasonable number of things. This list can never be comprehensive. How many variables we keep listing? There may be many more that we can always think of in terms of the physical properties, in terms of the kind of loads that we apply, kind of effect that is caused by those causations. So we can we can keep going over there, but I think we have a reasonable number of each of them to kind of now tell you what these columns actually mean. Let me. So the odd numbered columns are essentially your variables. So we'll call it as different kinds of loads, which is essentially your costs. What is causing this whole thing to happen? And the last one that you have on this end of the spectrum is the effect of that. So when you have a load, you essentially end up with some kind of a generalized displacement, or what you call as a deformation, for example. So let me call it as deformation to keep both rotational and lengthwise or translational kind of deformations both into picture, right? So that's the title of the last two columns, first and the last rather, the two ends. Now, as I said, the odd numbered ones are the ones that we are kind of talking of. All the first, third, fifth and seventh columns are all typically variables. Some variables might be given to you, some variables might be asked out of you typically in questions. So essentially the most interesting variables, or what you actually perceive, are the loads and the deformations, the cause and the effect. Sometimes the problem might be posed in an inverse manner. I want certain deflection to happen. So what is the force I have to apply in order to make it deflect by a certain amount or rotate by a certain amount? What is the moment that I have to apply? So in either case, It's like the chicken and egg story in terms of what is the cause and the effect if you're putting it in an inverse form, but essentially that is what is typically perceived as the main purpose of structural analysis. But if you try to go with just these two columns of variables, it becomes very difficult to kind of connect them, because a lot happens in going from the cause to the effect in terms of the physics involved and the math involved. So you introduce certain quantities which are less intuitive compared to the load and the deformation, and that's what you see in the third and the fifth columns. So let's call them as in general as stresses and strains. Sorry. Okay, so now you start seeing something falling in place in terms of being able to connect, because you have introduced two intermediate quantities. Now you don't need to directly connect load to deformation, which is anyway of your interest eventually, but you can do it in stepwise manner and then reach the final connection between the load and the deformation. So how do you go about it? Very easy to relate these two quantities, the loads and the stresses. So which is what all these things that you talked about, in particular Newton's laws and Euler's laws and the associated boundary conditions with them, are all what are typically known as equilibrium, right? So essentially you're trying to equilibrate either statically or dynamically, in which case you bring in the mass into acceleration, etc. But you're essentially trying to equilibrate these two things, right? So this is essentially what we call as the connectivity between these two is in terms of the equilibrium equations. When that equilibrium is at every material point in the body, then you call it Newton's laws or Euler's laws, and when it is just on the boundary points, you call it the natural boundary conditions, because that's involving forces and moments being specified at specific locations x naught, y naught, z naught. So essentially that's what you're doing in terms of the equilibrium over there. Okay, next, so we are trying to march from the cause, what we think as the cause, to the effect, from the loads all the way to deformation, and we said it's difficult to do that in one step, in one leap. Therefore we are doing it in small steps. So we introduce two quantities to start with, stresses and strains, and then we are trying to march on. First march has already happened, going from load to stress through equilibrium. What relates stress to strain? What is the which of course is representative of many of the quantities that you have listed over here. What is the law or equation which relates the stress to the strain? What do you call that?
Is it like just like constants?
Mm-hmm. So what do those constants depend upon? If I change something, will that constant change? Because constant means it should not change, right? So if I change some aspects of the structure, does it change?
Is it like material properties?
Exactly. So it's essentially material property. Another name, which is the technical name for this, is essentially what you call as the constitutive law, right? And already Nilesh brought out a very, very important point as far as the constitutive law is concerned, that it is dependent on the material. And many of these quantities that we have listed over here, you will see, are essentially material properties. There are certain things which may not be purely material properties, but have some material property built into them, right? So this is dependent on the material. What about the equilibrium? Does it depend on the material? The law itself, the law of equilibrium? No, right? So it has nothing to do with the material, right? So it's essentially something that works in our universe. These are laws that work under certain assumptions, of course, like inertial frame of reference, etc. But essentially these are universal laws, or what we call as natural laws. And now you see the reason why we call these boundary conditions natural boundary conditions, because they are expressing an equilibrium at the boundary, but equilibrium in general is a natural law. Okay, it's a law of nature. In particular, the Newton's third law, very, very important, and which is something not only in mechanics but also other fields of physics like electromagnetics and thermals, etc. You can always look at that equilibrium. So equilibrium thermodynamics is a big topic under thermodynamics, for example. So essentially some kind of an equilibration is being done, and that equilibration is not necessarily a static equilibrium. It could be a dynamic equilibrium as well, where you're bringing it into picture certain fictitious or pseudo forces, like you can call minus ma, minus mass times acceleration, as a D'Alembert's force, for example, and then you essentially are equilibrating. But essentially these are laws of nature. Okay, so whereas the constitutive law depends on the material, this is essentially natural or universal, so it depends on the laws of nature. Okay. Final, we are just one step away from completing this whole thing. We have already named 6 of the 7 columns. What do you think is this relationship? And remember, I have not only got you strains and deformations, but also we listed out a few other quantities as well. Forget this for now, but essentially you're talking of geometric boundary conditions over there and certain things which are related to the geometry in some sense. As I said, this MOI is different from this MOI. This is involving the masses. This is not involving the masses. It's a pure geometric property, right? And frames of reference, etc. So what is it that relates the strain to the deformation? And in strains, remember, I've not only listed strains, but also we've listed velocities and accelerations, etc. If you look at it, what are these is essentially a derivative of this, or a differentiation of this, which gives this, right? So what you're doing is, for example, if you're differentiating a deflection with respect to space, you end up with strains. If you're because for example gamma 11 is dou u by dou x1, so you're differentiating with respect to a spatial variable. On the other hand, if you're differentiating with respect to a temporal variable, that is time, you end up with velocity. You differentiate it again, you get acceleration. So essentially you're going from deformation to strain through a differentiation, either with respect to space or with respect to time. Okay, so in the course on dynamics that you might have taken, what is all this thing where you start with in the course which relates just the velocities and accelerations to the displacements? What do you call that? It's not kinetics. What is it? Yeah. So that's precisely what this column is all about. So you have the kinematic equations, which are essentially defining your strain in terms of the deformation in some sense. These are generalized strains. Your velocity is an example of a strain in a time sense. Okay, so when displacement varies with respect to space, you end up with strain. Displacement varies with respect to time, you end up with a velocity. So you will see a lot of equations if you look at the dynamic equations and also the stress strain equations, strain displacement equations. You will see 1:1 correspondence. There's a lot of commonality between that. The analogies sometimes get really beautiful. You get lost in them in terms of trying to see how both space and time happen to be independent variables with respect to which things are changing. So if you understand things very well with respect to space, for example, if you just use those analogies, you'll understand how it changes with respect to time, and you will be able to extrapolate your understanding to dynamic problems. So that's why this relationship is very important, and these are in general called kinematic equations. So just like equilibrium depended only on natural laws, constitutive law depends only on the materials, and your kinematics in its most basic form depends only on the geometry. So geometry is what kind of governs that. And we are talking of both spatial and temporal geometry in that sense. So it's essentially The geometry is what governs your kinematic equation, and these are the three important things that are there, which pretty much every engineering or science subject is actually dealing with. There are certain materials that you're dealing with, so there's certain geometry that it takes into account, and then there are certain natural laws that apply to it. So that's essentially the interplay between kinematic equations, the constitutive law, and the equilibrium as far as our structural analysis is concerned. But you can see something similar to this in pretty much every one of your subjects. If you think of it from a holistic point of view, whatever tricky way in which professors might formulate or reformulate questions and give it to you, whether it's an oral exam or a written exam, essentially there is a cause, there is an effect, and you're trying to relate that, and there might be certain, typically in most problems, it may not be a direct result unless you're doing something very, very basic, but you might have to introduce intermediate quantities in order to simplify the steps, and then you start connecting the whole thing and things all fall into place. Okay, so that's essentially kind of summarizing what we've been asking for. So let me just go back to the questions to start with, and then we will summarize the whole thing, right? Yeah. We started off by saying what are the variables, okay, because it has to describe the state of the structure. Those variables are the loads, your stresses, your strains, and the deformation. So those were the variables that we were talking about, and you guys gave me a lot of examples for each one of them, right? Next, we looked at in terms of, can we classify all those variables that you have listed? Instead of putting them all together in one basket, I put them in essentially 4 baskets, which are the loads, the stresses, the strains, and the deformations. That's the classification that we have in terms of 4 categories that we can think of all these variables falling into place. And this is like a very basic course in structural analysis, but even when you do very high level courses, graduate level courses, or research in it, or apply it in the industry, you will see almost always all of these fall into place this way. There might be certain things which kind of involve multiple places, which is why, for example, I put certain quantities in more than one column, but more often than not, it will kind of fall into place in one of these baskets, right? So yeah. Then we said it's not just about 4 variables, because some of them might be known, some of them are unknown. We want to determine the unknown quantities in terms of the known quantities. So we need equations or laws governing them so that we can connect them and therefore solve for the unknowns in terms of the knowns, right? So which is why the 3 sets of equations come into place, which is what we have showed by the double headed arrows, the equilibrium equations, the constitutive law, and the kinematic equations. Okay, so next we will look at what do these equations, we know the names of the equations, that is the equilibrium, constitutive law, and the kinematic equations, but what do they depend upon? We already addressed that. We said that whatever the equilibrium equation takes a form, it essentially depends on the natural laws, okay, the universal laws that you have. And for the stress strain relationship to fall into place, you essentially need what is known as the constitutive law. So it depends on the material, right? So then, as far as the relationship between strain and velocity on the one hand and deformation of all kinds on the other hand, essentially you have the kinematic equations. What they typically depend upon is the space-time geometry that you have, which kind of helps you connect the two, right? So let's move on. So macro mechanics, modeling, yeah, let me kind of summarize whatever. It's kind of clumsy on the board, so let me put it on the slide so that things are much more clearer, right? So there are 4 important quantities which are used to describe the mechanical state of a structure, and these are what we called as, in terms of the column headings, we call them as loads, stresses, strains, and the deformation, right? Now we also want to relate them, which is what those arrows do, double-headed arrows. Sometimes you might know the stress, you want to get the load which causes that stress, or sometimes you given the load, then you want to find the stress resulting from that load. So essentially the arrow works both ways, which is why it's a double-headed arrow, and that's the case with the constitutive law and the kinematics as well, right? So this is what we called them. We call the first set of equations as equilibrium equations, the second set as constitutive law, and the third set, sorry, it's kind of got displaced. So this should come over here under the double-headed arrows, so that's your kinematics, right? Now this is at the interiority or every material point for that matter, but then there's something which is valid only on the boundaries, which we started off listing as the boundary conditions, natural, etc. So geometric boundary conditions, etc. So those also come as part of these double-headed arrowed quantities. So along with the equilibrium equations, you have what are known as the natural boundary conditions, which typically specify forces and moments at a particular location, either concentrated or distributed, as Patrick pointed out. And then on the equivalently, in the case of the kinematics, you have the geometric boundary conditions as to supplement the equations, because remember, both of these equations are in general differential equations, and to solve a set of differential equations you need certain boundary conditions, and which is where the equilibrium equations are typically solved with the natural boundary conditions, whereas the kinematic equations are typically solved with your geometric boundary conditions. And since we are talking in a generalized sense of strains including velocities as well, so therefore initial conditions will also come into picture over there in addition to boundary conditions. So even though it's common in mathematics to differentiate problems involving differential equations as boundary value problems and initial value problems, in some sense they are actually very similar to each other, just that you're replacing space as the independent variable with time as the independent variable, and many of the things will kind of fall in place, right? So then we also saw what these equations are kind of based on, and at the 3D or most basic fundamental level, they are all dependent on certain basic quantities. But then once we start doing dimensional reduction, which is required for a beam theory or a plate theory, then we will see that some of these things get mixed up, and we will see examples of that most probably in the afternoon class, but right probably even today in the morning session itself. So at least a few examples of that. So what is it based on? So the equilibrium equations and natural boundary conditions are essentially based on laws of nature or universal laws, which are essentially conservational in nature. Some kind of a conservation that is taking place, let's say of a momentum, translational or rotational, or a conservation of energy, etc. Some kind of conservation is taking place, because of which these are coming into place. And where there are dissipative systems, if you have ways of accounting for that dissipation, you can factor that in, and then your conservation laws will work along with those dissipation as the difference between the left hand side and the right hand side. On the other hand, your constitutive law is dependent purely on the material, whereas your kinematics and geometric boundary conditions, as the name itself suggests, essentially depend upon the geometry, the space-time geometry, to be in a more generic sense, right? So when we are moving from traditional kind of structures made out of metals which are isotropic, you typically have complications, like composites are used quite widely today. So but where is the difference going to come? Constitutive law is obviously the only one which depends on the material. Equilibrium depends on conservation, natural universal laws, whereas kinematics depends on the geometry. So obviously your stress load equations and your strain deformation equations, that is the ones in green and yellow, do not change at all when you go from metals to composites. So that's not something to be worried about at all. It's only the red on white that we need to worry about, because that changes once you change the material or the type of material in particular. So that's the difference between conventional materials, by which I mean typically metals, as opposed to composites, right? And there are two main reasons why these are different, and we've kind of touched upon them in a different context earlier on, but essentially these are the two features which make them different. One is, compared to conventional materials like metals, we no longer have a homogeneous structure, we have what is known as a heterogeneous structure, right? Or also called as non-homogeneous. And instead of an isotropic material, you have an anisotropic material. And we understand these concepts already from the assumptions that we have made. What it essentially means is that how the property varies or does not vary with respect to certain things. One is going from point to point in space. So essentially that's your non-homogeneous material. In going from point to point, at a point in direction to direction, then you're essentially talking about anisotropy. So in one case you're fixing the direction and changing the location. In the other case you're fixing the location and changing the direction. In either case, for the conventional materials there's no variation, it remains the same. Just that in the case of when you have multiple materials, of which composites are an example, but even you could have a bimetallic strip, for example. In one of the strips you have certain properties, the other strip you have different properties. So going from one point to another point within a strip, it is homogeneous, but going from one point to another point where the 2 points are in the 2 different metals of this bimetallic strip, then you essentially are talking about heterogeneity in a more macro sense. But in composites, it's at the dimension of the fibers, typically a diameter of a few microns, and therefore the heterogeneity is much more complex to deal with. But they have been used for so long that these have been tackled quite easily. So the easy way in which we tackle these two, we do each one of them in a certain way. For example, the non-homogeneity or heterogeneity, the way we do is that we know the material properties are going to change when you move from a fiber to a matrix. With just a few microns you move, you have very inferior properties of the matrix mostly, and then again you move a few microns, you are probably in a fiber and you have very superior properties. So how do you tackle this? By a volume averaged stress and strain individually, and therefore the relationship between stress and strain gets volume averaged as well, and therefore the fiber properties and the matrix properties go into it. This is essentially another way of saying the rule of mixtures, which you guys have already worked upon to, and Patrick has a code also to do that. So essentially that takes care of this, right? Seems like a very complicated problem, but once you introduce this concept, you are essentially talking about fairly straightforward way of handling that. Because remember, the stress and the strain basically at fundamental level are properties at a given point. Okay, they are not something that is of a large chunk of material. It's at each material point you have a certain stress and strain at a given point in time. So that means that when you are dealing with such microstructured materials, the way you're dealing with is not the actual stress or the actual strain at different points, but you're having an equivalent homogenized material, and then you're dealing with which is essentially a fictitious material, and then you're talking about the stresses and strains in it. When they are averaged, obviously the quantity which connects them is also getting that is the constitutive law is also getting homogenized in some sense, right? The other thing, more complicated issue, is properties at a point varying from one direction to another. We know along the fiber direction its properties are usually typically superior compared to perpendicular to the fiber direction, and therefore what we did was, instead of just using a single E, single G, single nu, we introduce subscripts there to take care of the 3 different directions. You have E1, E2, E3, you have G12, G23, G31, and similarly nu12, nu23, and nu31. All of those essentially, those subscripts take care of the direction dependent properties of the moduli. So that's the Young's moduli, shear moduli, or the Poisson's ratio. They're all taken care of because you have an orthotropic material. You don't need to have infinite such quantities. Generally anisotropic material, you could have infinite such quantities, which is very rare, not found in nature typically, or engineered materials. You typically have given properties along 3 directions which are not collinear or coplanar, then you can get properties in any other direction, which is a combination of those 3 directions, which is why we introduce this concept of the direction dependent moduli. So are there any questions so far on what we have done? Yeah, it's clear? Yeah. So you will have a homework along with what was given the previous class to both to be presented next week, and that would involve to have a more complete listing of these variables. Go back, check your statics or dynamics or deformable body questions, your exam papers or the subject matter, and then list out a few more variables and try to make it a little more comprehensive. I'll give you a very descriptive way of this particular question. In fact, did I already post it? No, right? I didn't post it, right? So I'll do that this evening. So I'll post that question so that you're clear of what to do. So essentially, it's a much more prettier thing than my crazy handwriting over here. You're trying to get things a bit more organized. Is what I would like you to do. It might seem like a superficial exercise, but trust me, a lot of students in the past have benefited from this. People who have gone on to the industry, people who have gone on to become faculty members in top universities in India and abroad, they all continue to teach this particular way, which is kind of unique, I feel, from our lab, the way we try to portray this. And that has helped a lot of students understanding to develop to such a level that they have had huge productivity increase once they start thinking on these lines. Okay, and don't be scared to kind of populate certain things in multiple places, which is what I also did for some of the variables, because you really don't know exactly, they don't fit into a basket. So because they are typically derived quantities, if they are fundamental quantities, they will always fit into a specific basket. But if they are derived quantities, then you will see that they don't fit into a specific basket, and you will have to make sure that you have some kind of a logic where you're putting them, or multiple places that you're putting them into. Okay, so now things will become a little more clearer when we take up an example, and the simplest example that we will take up is like this. Let me draw that. In the homework that I will upload as a PDF, I will also give you certain links to videos of past students who have helped me with this exercise as well, and you will see some more variables than what you have listed, and probably some variables which you listed may not be there. Doesn't matter, as I said, listing can never be comprehensive or complete, but that will give you an idea of more examples for each one of them. So that way, if you just take a look at certain parts of that video, it might help you in your homework to do it much better, right? So as I said, we now want to move to an example of this, and for that we will take up the case of a rod of some cross section. It's a prismatic rod in the sense that every cross section, wherever you cut it, it's going to have the same shape and size. So it's going to have the same shape and size, though I may not be able to redraw the same thing exactly, but essentially that's what it is, right? Now, since it's a rod, by definition of many books, you're essentially subjecting it to a tension. That is what it means, and then you're applying a force F and a force F over here as well. And since we are going to kind of, this is a very simple problem, but we are going to kind of take the learnings forward to more complex problems which are part of your syllabus in structural analysis. So therefore, even though it might have done okay to just stick with F alone, I want to introduce a coordinate system, and let me call that as x1 along the length, and therefore a force component which is along that x1 direction, I will not just call as F but as F1, and maybe in a later problem we will have F2 and F3 to talk about as well, but here we have only F1. So that's essentially a load that you're kind of applying, and then as a result of that, you know very clearly that this is going to have some kind of an extension. And it's going to essentially change in length by delta L. The original length was L. And that change in length divided by length gives you a reasonably good approximation to the extensional strain, though strain can have many different possible definitions, as I said, but this is the definition that you have used in your homeworks already, and this is what we will stick to in our course as well. So essentially we are talking of delta L by L as the strain. Now let's put all of this into perspective from the table that we already listed. So we are supposed to have a load, we are supposed to have a stress which is caused by that load, a strain which results because of that stress, and because of the strain you have a deformation in some sense. So this is what we would like to look at this example. So what is the load in this example? Yeah. So we've given it a name F1, right? So it's essentially a tensile force, so that this is what we are talking about, F1, right? And what stress would that cause? Remember, we thought of stress as a matrix, sigma ij, and then we also showed that it is when no body moments exist, you have a symmetry, and therefore only 6 of those components remain. 3 are normal stresses, 3 are shear stresses. So in this particular problem, if F1 is acting through the axis of this cylinder, by which I mean a point going through the center of mass. So if I take a point which is the center of mass of this, and I'm applying the load through that. Okay, so though to be more precise, I have to define what is known as a tension center. As many people are aware of a shear center, but most people are not aware of this concept of a tension center. It's a property of the geometry, and we can determine that. But right now, let's say for this geometry, the centroidal axis or the center of mass happens to be the tension center, and therefore we have the loci of the tension center of each one of those cross sections. When they're joined, you get a line, and that line is what is getting extended by a certain amount, and that's what we are interested in. Because the way I've shown the force, remember, it's a concentrated force that I'm showing. So a particular point on the cross section is getting extended much more than other points on the cross section. But that's where what is known as Saint Venant's principle comes into picture. Saint Venant's principle says that if you go into the interior of the rod by an amount of the order of magnitude of the cross sectional size, then it doesn't really matter how I apply the force. I could apply a concentrated force, I could apply 2 concentrated forces which add up to the same value F1, or I can distribute F1 divided by A and uniformly apply it. As far as the interiority is concerned, about a diameter away from each end, you will see that the same results end up, irrespective of how I actually implement that in an experiment in terms of applying those loads. I can put it in a vise and essentially stretch the vise, so then you are essentially shearing at the edges over here. So locally the boundary condition might be in the form of a shear, because I'm gripping this and trying to pull it out, which is what I would do here also. I cannot directly pull this over here. I will try to apply a shear on the surface to pull it, but the interiority doesn't care whether I'm applying it as a shear or an actual force that I'm trying to apply to pull it. Either case, it's going to be the same. So for most parts of the course, we will not deal with these corners, the edges, what actually happens. It's much more complex. It's like in fluid dynamics, boundary layer theory or boundary layer aerodynamics is much more complicated compared to the aerodynamics elsewhere, right? So it's something similar to that. It's not that it's not handleable. There are lots of very good, well-established models already in place, but beyond the scope of this course. So almost all of this entire course will be focused on what's kind of happening in the interior, or another way of saying it is, it doesn't matter how I actually apply this force, but essentially what matters is the resultant of that force, okay, or resultant moments and resultant forces that might occur in a more complicated problem. So let's get back to populating this. So the 4 variables that we want, each of them have a specific thing. So we said that stress generally involves, in a general problem, not this problem, it involves sigma 11, sigma 22, sigma 33, the 3 normal stresses. Then you have tau 12, tau 23, tau 31. But in this particular problem, which of them will occur, which is kind of the dominant load in the interiors? Yeah. Because remember, in the notation sigma ij, I stands for the first subscript stands for the normal to the surface on which you're interested in the stress. What is the normal to the surface here? Because I'm cutting it perpendicular to x1, so obviously it is a unit vector b1, let us say, parallel to x1. So essentially that's why the 1 comes, the first one. The second one is which is the direction in which that force is acting, and that force is also acting in x1, and therefore the second subscript is also 1. Okay, all the other stresses for this particular problem are equal to 0, irrespective of whether this rod is made out of a composite metal, doesn't care, right? So remember, this particular relationship is purely a conservation law, so a natural law, and essentially you're talking about how these are kind of getting equilibrated with each other, right? So this is an applied external force, and this is something that is a resultant interiority. So this is actually Newton's third law coming into place. So what is Newton's third law saying? Every action has an equal and opposite reaction. So that's essentially how your sigma 11 comes. So you're trying to pull it this way, that material tries to pull it back, and they are essentially acting opposite to each other. And if you think of the load instead of a concentrated load as a uniformly distributed load, that's exactly the stress, applied stress, and the resultant stress are essentially going to balance out at any given element. If I take a small element over here, then you will see that it's essentially balancing each other out on both the sides, right? So that's the second variable. The third variable is the strain. Which strain? So just like the stresses, we have 6 strains over there, but not all of them are incited in this particular problem. Which one is the dominant strain? Yeah. So we will use the capital letter gamma now, because epsilon we reserved for the 2D problem. So which we say gamma 11 equal to epsilon 11 plus x3 times rho 11. So therefore we will stick to this notation, gamma for the 3D variables. Whenever I say something is a 3D variable, it just means that in general it could be a function of x1, x2 and x3, all 3 spatial coordinates. If it's a 2D variable, it's a function only of x1 and x2, right? So that is the strain. So that we got the third type of variable. The fourth type of variable is the deformation. What is the deformation that is happening in this particular problem? Yeah, so your delta L that is happening. So that delta L, of course, I'm indicating at the tip, but at any given point, the cross section, if it's at x1, it would have moved by x1 plus u1, okay? And that u1 happens to be at x1 equal to L, it happens to be equal to the total change delta L, okay? But at any point, at this point, for example, if I'm going to fix this end, u1 equal to 0. And u1 is maximum at this end, and it's going to kind of linearly vary as I march from the left to the right? So let me call that as u1, okay, which has a specific value of delta L at x1 equal to L, but otherwise it's a function of x1, okay. Because u1 is a function of x1, the other variables are all going to be functions of x1 in general, okay. But this specific problem, very simple problem, you will see that that functional dependency actually drops because you have just a constant axial force throughout the entire rod. So the stress and the strain would be constant as well, only the deflection varies linearly with respect to that, because you have a linear strain definition. That's the first derivative of u1 is going to give me gamma 11, and therefore you will see that it varies from 0 to delta L in a linear fashion, right? So now we are done with the variables, that is 4 types of variables: loads, stresses, strains, deformation. Now we want to connect them, equations, right? So we want the equation which connects the load to the stress. What is that particular equation called? Remember, it's the equilibrium equation, depends only on the natural laws. But here we are trying to relate 2 types of quantities. They are not dimensionally the same, right? If they were dimensionally the same, you would see that pure nature will take care of it. But now that on the one hand I am having a force which has a unit newtons, the other hand I have a force per unit area which is essentially stress. So therefore it's not just the nature which will play a part, but also the geometry to some extent will play a part. This is what I meant by when I said some cases there can be a little bit of haziness. This is an example where you see actually geometry coming into picture, even though geometry should not come into picture. It should come into picture only in this strain displacement relationship, which is the kinematics, right? But it's coming here because I'm trying to relate 2 kinds of quantities. I could have defined the same problem. Instead of saying I'm applying a force F1, I could have said, like what Patrick pointed out, an external pressure, which is of course compressive, but I can apply an external stress distribution, which is a uniform stress distribution at either of these edges, a sigma naught. Let us say instead of F1 I can apply, let's say, uniformly distributed stress, which is F1 divided by the area of cross section of this, which is A. So that I can call that a sigma naught is the applied stress, which is essentially nothing but your F1 divided by A, right? So then the load will be sigma naught, that whatever stress that I'm applying at the edges, and I will be relating sigma naught with sigma 11. I will be relating apples to apples, not apples to oranges, and therefore you would see in that case the equilibrium would just become sigma naught equal to sigma 11, okay? And that's pure natural law, that's pure Newton's third law. Every action has an equal and opposite reaction would come into picture. Why opposite? Because you will see that if I'm pulling this way, the stress, if I cut at any location over here and take a small portion towards the end, so here's where I'm applying the sigma naught, you will see that for this to be under equilibrium, I will have to get my sigma 11 over here, right? So this is sigma 11. Remember, this is an internal stress. This is the applied stress, okay? And they are just going to be equal and opposite to each other. You see that one is in positive x1 direction, the other is in a negative x1 direction. But in convention of forces and stresses in particular, we always define as tension is positive and compression is negative. So in that sense, they might look the same, but that's just a nature of our convention that is chosen like that. But otherwise, you see one is acting in the negative x1 direction, the other is acting in the positive x1 direction. So essentially they are acting in equal and opposite way. So that is what is law of conservation, which is purely nature dependent. But once you introduce 2 different kinds of quantities, you have to take care of the dimensionality between them. How a force is reduced to a stress is through an area. So that force divided by the area, in this case the area of cross section, which is what we call as sigma naught, and therefore they are essentially equal to each other, okay? So that's as far as your equilibrium equation is concerned. In this case, it just turns out to be a simple F1 is equal to A times sigma 11, right? Not that other quantities are not there. For example, you know, if there is a non-zero Poisson's ratio, which is the case with most materials that we use in aerospace structures, or for that matter any other structures, you will get sigma, gamma 22 and gamma 33 also, which will be the Poisson's ratio times whatever is gamma 11, right? So you will get the other strains, but right now we are looking at only the direct effect of everything that falls into place, whereas all the other stresses will go to zero. by equilibrium all of these go to 0, I cannot say the same thing about the strains. In an isotropic material, I know that gamma 22 and gamma 33 will be there. Okay, so here you will have a gamma 22. You will have a gamma 22 and gamma 33 which can be excited even in an isotropic material. But if you go to composite materials and it's a non-orthotropic material, principal material directions, you will still get only these two. But if it's any other direction other than the principal material directions, then you will get the other strains as well, the shear strains as well. They can also be excited because there can be a coupling between shear and the normal strains. So therefore you would see in general all the other strains can be there, but this is the direct effect of this. So that's what we are trying to look at in this simple example. So what is the relationship between sigma 11 and gamma 11? Stress strain relationship. Hooke's law, yeah. So in a composite, of course, it would be the generalized Hooke's law. So you would have your sigma 11 related to your gamma 11 through E1111. So the first 11 stands for the stress component, the second 11 stands for the strain component. So essentially, instead of a second order tensor, you have a fourth order tensor, but we will keep those things besides the point over here. We're essentially saying there's a certain constant which depends just on the material. Okay, so of course in the case of the simplified Voigt notation, VOIGET, which we introduced where we had just 6 by 6 and therefore we are talking of C11, C22, etc. instead of the EIJKL. There you would just put the C11 as essentially relating these two, right? So that's your stress strain relationship, so which we called as the constitutive law. And what did we say? Equilibrium depends only on the natural laws, but your constitutive law depends on the material, right? So you already see that what is the connectivity here between the stress and the strain? E, and E is a pure material property, right? So it depends only on the material, and you can already see that happening over here, that it's coming in the form of the Hooke's law coefficient, which is constant of proportionality between the stress and the strain, right? So now we come to the last of the equations, which we called as the kinematics, to take care of dynamics problem also eventually, but right now our focus is on the statics equation between gamma 11 and U1. What is that relationship? Simplest form. How is the strain defined in terms of the displacement? Yeah, because the U1 is a linear function over here, but in a more general sense, if these are arbitrary functions of x1, how would you get gamma 11 if I give you u1 of x? Suppose I give you u1 of x1 as, let's say, sine x1. How will I go about determining gamma 11 of x1? Yeah, that holds if it is a constant strain or a constant or a linearly varying displacement. Then what you're saying is true, which is in fact the case over here for this simple problem. But I just want to get it in a more rigorous mathematical sense. How do you define strain in terms of displacement? The general definition for strain displacements. Yeah, so calculus is involved, but what's the reverse of the integral? Derivative. So what derivative of what equal to what? This problem. Only two quantities I want to connect, gamma 11 and u1. If you want to think of this as epsilon 11, maybe you'll remember. Yeah, absolutely. So you have du1 by dx1. In this particular problem, everything varies with respect to only x1, so I can write it as a ordinary derivative. Otherwise, I'll have to put it as a partial derivative dou u1 by dou x1. But essentially, it's connecting, so that's equal to gamma 1. So gamma 11, let me kind of, so gamma 11 equal to this, okay. So this is one equation, this is the second equation, this is the third equation. So we have now tried to connect the cause to the effect, the load to the deformation, that is F1 to U1, if we can substitute these one into the other. Now I can eliminate gamma 11 by substituting this into this equation. So I can substitute for gamma 11, so gamma 11 is already gone. So now I have sigma 11 in terms of U1. Then I can substitute sigma 11 over here to get F1 in terms of U1, which is what I started off wanting to do, right? So when you do that, you eventually end up with connecting these three. So let's look at it in a more organized way in this slide, and then we will break for lunch. Yeah, so this is the first type of member as an example that we are looking at in the sense of an axial bar or column, and the examples we have already seen in the first half of this course, where we looked at stringers in the wings or in the fuselage or even in the tails. Those are all essentially having either a tensile or a compressive load. So many of the things that we are going to say here are going to be valid even if I change the direction of F1 and put it the other way around, as long as F1 is within certain limits, because it should not cause buckling and instability. As long as if F1 is below the buckling load, almost all that we have shown over here will still be valid, just that the F1 value will be negative, and therefore sigma 11 will be negative, gamma 11 will be negative, and U1, instead of causing an extension delta L, will be causing a contraction delta L, and that's essentially a negative displacement that you have. So everything becomes negative, but the equations remain very, very similar. So now that's the example that we have, stringers in wings and fuselage and tails, and as always we have four quantities used to describe the mechanical state of stress, which is a load, stress, strain and deformation. And in this particular example, that load happens to be your F1. That is, the F1 is the load that we have applied on either side, is a constant cross-sectional area that you see over here. And then you have you see the stress, corresponding stress that is incited or excited because of that is your axial stress, which we call as sigma 11. Same thing what we did in the whiteboard. And then coming to the strain, you end up with an axial strain, which is your gamma 11. I use the wrong notation over here, epsilon 11, but it's essentially gamma 11. And then the deformation, which is the axial displacement that you have here, which is your U1, right? Now, then we went on to getting the relationship between them, the equilibrium equations between the load and stress to start with. The load, which is F1, and the stress is sigma 11. Therefore, the relation between the load F1 and sigma 11 is through that particular area. And as I said, truly speaking, this should be only dependent on the nature's laws. But because we are using different kinds of quantities, we have to bring in the area. Okay, if we had specified the load also in terms of a distribution, force per unit area, then you would see that only nature enters, geometry doesn't enter into picture, right? Next, we wanted to relate the axial stress to the axial strain, and as Nilesh pointed out, we invoked the Hooke's law over there. And then we got this 1 by E times sigma 11 is equal to epsilon 11, right? Now finally you have this epsilon 11, which is your dou U1 by dou X1, and because we are dealing with only linear strain displacement relationship. Truly speaking, this will have quadratic terms as well, and this is something very, very common in aerospace structures, because large displacements are involved, and therefore you cannot just stop with linear derivative. That's the first derivative. You will have higher order dependency, and that is going to make this equation nonlinear, and that's almost always the case with aerospace structures. But as far as this course is concerned, we will make that erroneous simplification that you can use a linear relationship between gamma 11 and u1, which is over here. All we did was to substitute this for epsilon 11 here and bring your sigma 11 here. So we are eliminating both these intermediate quantities. Remember, we've always been saying that the load is the cost, the strain, the deformation is the effect. Okay, but we introduced two intermediate quantities, the stress and the strain, right? Now we want to get rid of stress and strain. Now that we have all these three equations in place, we are substituting each one into the other, and finally we end up with this particular equation, which gives you the load in terms of the displacement or deformation u1. So we've got what we wanted to relate the cost and the effect, that is F1 and U1, and the relationship between them is actually a differential operator and also involves a certain constant, which is EA. And now you see that all these things, because we have combined, these things are all falling into place together. A is entering as a geometric parameter and E is entering as a material parameter, and you will find this almost always in all the other examples that we will see in the afternoon also. There will be a material contribution, there will be a geometric contribution, and both of them in some sense are offering a resistance to the costs and trying to keep the effect as small as possible. So the higher the EA, you're going to have lower values of U1 at any given cross section at particular value of x1 along the length, including at the end where it is delta L. That delta L will come down if you increase your EA. So your EA therefore in this problem, because it's an axial load, axial stress, axial strain and axial displacement, is called as axial stiffness. So axial stiffness is EA, and that falls into place into our bigger picture, the big canvas as well. And we see that this is, first one is a material property, the second one is a geometric property, and both there are many ways in which you can make the displacement low over here, by either by increasing E, which means that you use a material with higher Young's modulus and therefore you have a larger EA, or by using a geometric change whereby you change the size of the cross section, which is essentially changing your A. Okay, so there are certain other subtleties with respect to this particular problem, which will resume in the afternoon session, and then we will take it on to other examples as well, all of which will fall into this paradigm that we have introduced. Thank you.